Hi guys, Dr. Kruse. This is elementary statistics. In this video, it's going to be hypothesis testing using kind of the old-fashioned method, the traditional method, where we shade a critical region and then we see if our test statistic lands in that region. For this example, in this video, sigma is unknown. The population standard deviation is unknown. Now I'm going to go, a little bit faster in this video. I did do a detailed 5-step approach to hypothesis testing in the previous video. So if you're not familiar with the 5-step hypothesis testing method that I use, just go back to and look up the video hypothesis testing, critical region traditional method, sigma known. All right. If you change that unknown to known and look up that video, I spend a lot of time explaining the 5-step hypothesis testing method. This video, I'm going to assume that you already know the 5-step procedure, so we can move a little bit faster. All right, now remember what we're doing. All right, we're going to construct a curve, and I'm going to shade in the area where I can reject the null hypothesis. So this is called the rejection region or rejection area or critical region. That's where that name comes from here, critical region. All right, I'm going to shade in the critical region where I'm able to reject the advertised claim or the accepted belief, the null hypothesis. Now today we don't know what sigma is, so we're going to have to use t-values instead of a z-score. So I'm going to have to figure out where to draw the line here. I'm going to have to look that up in the t-table, figure out where to draw the line, shade to the right, or if I'm over here, shade to the left, or shade both tails. Just depends on your hypothesis. And I'm going to shade my critical region, and then I'm going to do a test statistic. So using my t formula, I'm going to run a test based on my data, and I'm going to place the results of my data as a dot somewhere on this x-axis. Now, if that dot, that test statistic, lands here in the shaded region, I get to reject what they said. I can reject the null hypothesis. I can say, no, you're wrong. But if my test statistic lands anywhere over here in the white area, then I have to accept their claim. I have to accept the null hypothesis. Technically, we say I failed to reject the null hypothesis. All right, so let's work about 4 problems where we don't know the population standard deviation sigma. All right, they'll give us the population average, that's called the mean, but they won't give us the population standard deviation, that's sigma. And when they don't give us the population standard deviation, we have to use the t-table and come up with a t-value instead of a z-score. So let's just run through this problem real quick. This is just an explanation of t-values and degrees of freedom. Remember, degrees of freedom is 1 less than whatever your number is. And there's a really long-winded explanation of what degrees of freedom means. You can Google it if you care. Basically, 60 of these values can be whatever you want, but the 61st value is not free to vary. So degrees of freedom mean 60 numbers can be whatever you want, but the 61st number needs to be fixed to make everything work. You guys can Google that if you want to. Okay, here's the problem. Pyramid Lake is on this reservation in Nevada. The lake is famous for trout. Suppose a friend tells you that the average length of trout caught in Pyramid Lake is 19 inches. All right, that's the advertised claim. That's what is believed. A friend tells you, all right, that's an accepted belief. That's an advertised claim. Or sometimes they just come out and call it a population mean, and they say mu is believed to be 19. It's just something that all the fishermen around there accept. They accept that the average length of a fish in that lake is 19. Well, we're going to challenge that belief. We're going to say, no, it's not 19. We could say the average is less than 19. I could say the average is more than 19, or I could simply say the average is just not 19. But we're going to challenge the belief that the average length is 19. All right, it said, however, a survey reported that of a random sample of 61 fish caught, so the number of fish that were caught was 61, the mean length of that sample, we call that X bar. So this is your sample. You're running a test. You're running a challenge to the accepted belief that the average length is 19. You're going to challenge that. So you grabbed 61 fish. You measured their length and averaged it. And you said the average the average length of my 61 fish, when I added up all those lengths and divided by 61, the average length was 18.4. Well, that's this data over here. This is what's believed to be true. We believe the average fish is 19 inches, but my data, my average is 18.4. Now 18.4 looks like less than 19. The question basically is, when you're doing hypothesis testing, is it less enough that anybody cares? Is it significantly less? You know, if you come up with an average of 18.9, well, that's close enough to 19 that nobody's going to care. We say your data is insignificant. But if you come up with something that's way, way, way lower or way higher than the accepted belief, well, now your data is significant. So we have to run a test and see whether our data is significant, if our data is different enough that anybody cares. All right, and they gave us the estimated standard deviation of S equals 3 inches. That's our give or take on our sample. So on our sample, our average length was 18.4 inches, give or take 3 inches either way, standard deviation. So this is my sample mean, sample average, and this is my sample standard deviation. All right, do these data, that they're talking about your data, your 61 fish that you caught, do your 61 fish indicate that the average length of a trout caught in this lake is less than, there's our clue for our hypothesis, less than 19 inches? So they're telling us, they want us to challenge 19 by saying, no, the average is much, much less than 19. Use a level of significance, alpha, of 5%. That kind of tells us how to draw our picture here in a minute. Solve using the traditional method, the critical region method. That's what we're going to do. All right, so the first step in almost every hypothesis testing method is to list your hypotheses. Now H sub 0, that's 0 means null, that's the null hypothesis. This is the accepted belief or the advertised claim. So they said on average the fish in this lake are about 19 inches. That's their claim, and you're going to challenge it with H1, called the alternate hypothesis. This is your challenge. You're going to challenge the accepted belief that the fish are 19 inches. And they told us to phrase it so that it is less than. All right, so our challenge is no, no, no. The average is not 19. The average is actually less than 19. This is our challenge, and we're going to test it and graph it and make a decision about whether our data is significantly lower than 19. If it's just a little bit lower than 19, nobody cares. It's insignificant. But if it's a lot lower than 19, then that's significant. And somebody's got to, change the signs around the lake and say, well, the average is not 19 anymore. Now the average is much lower. That's what we're trying to figure out. All right, second step in my process here is to draw a picture of kind of what you're after. Let me cover up that T star for a second. All right, so draw a picture of what you're after. So they said use an alpha level. That's a significance level. This is my rejection region. So they want a rejection region that is 5% of the curve. And if our alternate hypothesis is less than, then we're going to shade the left tail of the curve. How much of the left tail? 5%. So I need to figure out what T number gives me an area of 5% here. So if there's 5% here, there's 95% over here. We always look up area to the left, all right? So I need to look up, pretend you don't see this number right here. I need to look up what T number gave me an area of 5% of the curve to the left, all right? Now, lots of times, we usually go forwards. Usually we know the T number and we look it up in the table and it tells us the area. Well, I'm going to go backwards. I know the area and I want to figure out the T number that produced that area. Probably the easiest way is to go to the table. Now this is the table I'm using here. So I'm looking for a one-tailed area. I want that left tail shaded in, and I want to shade in 5% of that left tail. So I follow this over to 5%, 0.05, and then I follow it down until I hit the degrees of freedom that I'm looking for. And I want 60 degrees of freedom. So all the way down, 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 down to 60 degrees of freedom means I start shading at 1.671. Now I'm on the left side of the curve, so I'm going to shade at negative 1.671. Okay, our table told us the number 1.671. That's over here. That's where I would draw the line if I had a right-tailed test and I wanted to shade 5% to the right. But you got to think about where you're at. You want a left-tailed test, so you don't want the 1.671. You want the negative 1.671. You want to be, whoops, I'm pointing to the dot. I mean to point to the line. You want to be over here. So you draw the line at negative 1.671 and you shade to the left. Now the next step is to run your test. All right, we have our data, our X bar, our average length was 18.4. I'm going to find the difference between that and what the accepted average length is. So 18.4 minus the accepted value of 19, mu, divided by standard deviation. That's going to change this to a 0, 1, 2, 3 number in most cases, because I need to place it on this graph somewhere. And to place it on this graph, it needs to be a 0, a 1, a 2, or a 3, or the negatives of the same numbers. All right, so I'm going to take my raw data, my 18.4, and I'm going to convert it to a 0 or a 1 or a 2 or a 3 kind of number. All right, so we find the difference between what I found and the accepted belief, and I divide it by standard deviation to see how many steps left or right I got to take. Now, standard deviation is adjusted a little bit for your sample size. That's what this part is right here. We're just adjusting the sample standard deviation. So I do the calculation, and my test statistic, the little star there, means it's the test statistic. It's the dot. It says you need to take about 1.5 steps to the left. So I take 1 step to the left and about a half of a step more, and my test statistic is going to land right there. You just put a big old dot right there. And this is a visual of whether you're going to accept or reject the null hypothesis. This is the rejection region over here. This is kind of where you win. If your test dot lands over here, you win, and you get to say, I reject what you said. I reject your null hypothesis. I reject your claim. Unfortunately, in this case, our test statistic, our data, didn't quite make it to the rejection region. So in this case here, I have to say I was wrong. I have to say, okay, all right, I can't reject what you said because I landed over here in the white. So I have to basically accept what they said. All right, now we can't say it the easy way. We can't say I accept your claim. You know, they claimed the average length was 19 inches. I was arguing that it wasn't. So I'm wrong. I didn't quite make the rejection region. So I have to say, I was wrong. I accept your claim. I accept your null hypothesis. That's the easy way to say it. But of course, we don't do that. We say it the hard way. And we say, I tried to reject what you said, and I failed. Failed to reject what you said. Failed to reject the null hypothesis. And then step 5 is just interpret your conclusion. Step 4 is your conclusion. Reject HO or fail to reject HO. And step 5 is just explain your conclusion in terms of the problem. Now, the way I explain it, I just use all the exact same words until I get to this word that. All right. So if I'm failing to reject the null hypothesis, that means that I did not have enough evidence to prove the claim wrong. All right. There is not enough evidence at the 5% level of significance to conclude that. Now, after this, we just kind of restate what our challenge was. And our challenge in this case was we were trying to challenge that the average fish length is less than 19 inches. That was our challenge. But we failed. All right, we failed. Our challenge failed. I do not have enough evidence to prove this claim here, this challenge. All right. Now, if it had gone the other way, if I was able to reject HO, the only thing I would change in this whole paragraph is I would change is not to is. All right. If I was able to reject HO, I would say, haha, I have enough evidence. There is enough evidence at this level of significance to conclude that the average length is less than 19. All right. So you got two different cases. Your interpretation is going to be identical, word for word, except for is or is not. I did want to make a little mention here about the t-table. You'll notice that if your group is small, like 6 degrees of freedom, that would be a group of 7, well, then your rejection region, your critical value, could be 5.9 steps to the right or 5 steps to the left, 5.9 steps to the left. That can be a pretty, wide curve. Usually we just, with a standard normal curve, we go 3 steps right and 3 steps left, and that's almost everybody. But if you just have a group of 7, which is degrees of freedom 6, well, your curve would have to go like 6 steps right and 6 steps left. But just kind of watch, what happens as your group gets bigger and bigger and bigger. If I get down to a group of 21, which would be degrees of freedom 20, now I'm just going to go 3.8 steps left or right. And then the bigger your group gets, we get down here to groups of 60, 70, 80, or degrees of freedom 60, 70, 80. And now we're down to 3.5 steps right, 3.5 steps left, 3.3 steps left, and 3.3 steps right if you sample 501. So the more people you sample, or the more samples you draw, the closer your t-value gets to a standard normal curve. All right, random sample of 46 coyotes, that's n, which means degrees of freedom is 1 less. And northern Minnesota showed the average age of my sample. So I trapped these 46 coyotes. I'm making my own sample, and I averaged their age to be 2.07 years. So my sample, the ones that I could catch, those 46 that I could catch, their average age was 2.07 years. With a sample standard deviation of s equals 0.77. So here's my sample data. This is my sample average and my sample standard deviation. However, it is thought, now this is the accepted belief, this is the advertised claim, it is thought that the overall population mean, there's mu right there, that the population mean age, average age of coyotes is 1.75. So they're saying the accepted belief, the population mean, is believed to be only 1.75 years. And they don't tell us sigma, they don't tell us population standard deviation, so we're going to use the t-table and get a t-value for this. If they told us this, we would use the z-table. If they don't tell us this, we use the t-table. So look at what is believed to be true, and look at what I actually measured with my 46 coyotes. It looks like my group of coyotes live a lot longer than what was believed to be true. So my challenge is probably going to be, hey, I don't think this is right anymore. I think that they actually live much longer. So that's probably going to be my challenge, but we have to double check the words and make sure that's what they want us to say. All right. They could say, I believe they live much longer, or I could just say, I believe that the average is different from 1.75. So let's just read here. Do the sample data indicate that coyotes in this region tend to live longer? Okay, so they are going to challenge that. It looks like coyotes are living longer than what was thought to be. And use a level of significance of 1%. All right, set up your hypothesis. So the null is what people believe to be true. It is believed, it is thought that coyotes live about 1.75 years. But my challenge is, my alternate hypothesis, I challenge that and I say, I took my own sample, I caught 46 coyotes. I believe that the population average is actually much higher than 1.75. Now remember, it's got to be much higher. It's got to be significantly higher to matter. If I just get something like 1.76, yeah, that's higher, but it's not enough to matter. I need to get something that's significantly higher to matter. All right, so next step is draw your curve. All right, remember this is a t distribution, and the t distribution is kind of wild. It can go 5 or 6 steps right or 5 or 6 steps left, but the more people or coyotes or whatever that we sample, the more normal the t distribution looks. All right, I want a 1% significance level. That means I need to shade to the right, because this is greater than's over here on the right side. I need to shade 1% of the curve, all right? 1% of the curve. That means there's 99% of the curve here in the white, and there's only 1% here in the tail. And I got to figure out exactly where to draw this line. So when you're trying to figure this out, you don't actually know where that line is until you look up that t number. So let's grab our table. And I'm going to look up a one-tailed test. All right, one-tailed. If it's less than or greater than, that's a one-tailed test at a 1% level of significance for degrees of freedom 45. All right, a one-tailed test, one-tail area, and I want the area to be 1%, that's 0.01, and I want to follow that column down to degrees of freedom 45. Down, 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 and it looks like it's 2.412 is where I would draw the line. All right, so I have figured out that for 1% of the area to be shaded to the right, a right-tailed test, to shade in 1% of the area, I need to draw the line about 2.4 steps to the right. Here's 0, there's 1, there's 2, there's 2.5, so it's just short of 2.5. So about 2.4 steps to the right. I want to shade to the right. That shades 1% here and leaves 99% in the white. All right. All right, I do want to show you, just by the way, you can look up this 2.412 number right here. You can look up this t number in your calculator if you want to, and if you have an 84. The 83s, it's really more trouble than it's worth to look up the t number in an 83. You can Google it if you want to, but if you have an 84, it's real easy, because what you're looking for is you're going to put in the area and ask the calculator to go backwards and tell you what the t number is. So what I want is, I want distribution in blue right there. So second, and I want distribution. All right. What I want is called a backwards t. That's inverse t. Inverse means backwards. So by pressing inverse t, I'm telling them I'm going to give you the area, and you go backwards and tell me what the t value was. So I choose that, and it says, okay, what area do you want? Well, I want 1% over here, so 0.01. And then it says, what are your degrees of freedom? Our degrees of freedom were 45. We had 46 coyotes, so degrees of freedom is 45. And then after that, we paste it into our calculation window, hit enter one more time. And there's your negative 2.4121. Okay, now why is it negative? All right, because I actually put in the wrong value. I told it to calculate 1%, and it always calculates area to the left. I messed up. So I told it, calculate 1% over here, and it says, okay, well, for that, you would need to draw your line at negative 2.41. Let me try and do it correctly. All right, what I actually want to ask it is, I want to draw this line right here. I'm asking it, where is this line right here? Well, I got to put in how much of the curve is to the left. I should have put in 99% of the curve is to the left. So let me try it again and fix it. So second, distribution, I want backwards t, inverse t, and I put in the wrong thing. I should have put in 99% of the curve is to the left. Degrees of freedom is still 45. Paste it into your window, hit enter one more time, and there I got the right number. All right, so with the 84, calculating t is pretty easy, but honestly, it's probably faster just to use your table. All right, and if you have an 83, I wouldn't try to do this on the 83. It's unnecessarily hard. Okay, we got to run our test and see how our data ended up. I'm going to figure out what where my data stands, in relationship to the understood average. I'm going to place that dot here on the x-axis, and I'm going to make a decision about whether I have to accept what they said or I get to reject what they said. So t star, that's my test statistic, is 2.07. That's what I came up with. Averaging my coyotes, I got 2.07, minus the accepted belief of 1.75. This is mu. This is what is thought to be true. This is what I found in my test. And then divided by standard deviation tells me how many steps to take to the right. All right? Remember, dividing by the square root of n, that's just an adjustment. We have to adjust standard deviation. All right, it tells me that I need to take 2.8 steps to the right. There's 1 step to the right, 2 steps to the right. There's 3 steps to the right, so 2.8 would be somewhere in there. I put a big old dot there. Your t star is going to be a dot. And then I look at it and make a decision. Well, I landed in the rejection area. This is the critical region, this shaded area. I call it the rejection area because I get to reject. This is the critical region, and this 2.412 was my critical value. The T star is my test statistic, if you want to write down some vocabulary. One more time, this shaded in area, that's the rejection region, also called the critical region. This line that we drew to start coloring, that is called my critical value. And then the dot that I place on there, the T star, that's my test statistic. Just vocabulary there. I get to reject, so I win this battle. I said that these coyotes live a lot longer than what was thought to be true, and it's so much more that it's significant. All right, so I get to reject the accepted belief. And then I just spell it out, and notice all the words are basically the same. There is enough evidence, see, because I won, I get to reject what they believe. I have enough evidence at the 1% level of significance to conclude that, and then the rest of it is just what your challenge was, using the words from the story, to conclude that the coyotes in this region of northern Minnesota live significantly, I like to throw significantly in there, longer than 1.75 years. It's not just longer, it's significantly longer. All right, let's do two more real quick. All right, so this is talking about plasma, level of acidity of the blood. It's believed to be 7.4 if you're healthy. The mean, the average of all healthy adults in the world is believed to be 7.4. This is the claim, the advertised claim, the accepted belief. So mu is believed to be 7.4 if you're healthy. All right, we took a sample of 36. N equals 36, which means degrees of freedom is 35. And they took this drug, blood test showed that this sample, these 36 patients, their average level was 8. So our sample, our 36 patients, their average level was 8 compared to what was believed to be normal. It is believed that healthy adults have a level of 7.4. My adults that I sampled and measured have a level of 8.0. That appears to be higher. Let's see how we're going to phrase our challenge. They gave us sample standard deviation of 1.7. Now this is a little difficult here. Alpha is 5%. They said use a 5% level of significance. I'll get to the alpha divided by 2 in just a second. Let's phrase our hypothesis. So the null hypothesis is what is believed to be true. It is believed to be true that the healthy adult will have a level of 7.4 of whatever they're measuring. My challenge is different from 7.4. Now, where did I get that? You just have to read the words and figure out what they want to do. It usually comes after use a test and test whether it has changed, and they'll either right here they'll say lower than, more than, or if they say either way, it could be higher or it could be lower. That just means different from. So my challenge is, no, the average is actually different from 7.4. Even though my data shows that it's higher than 7.4, I'm just simply going to claim, well, it could be higher, it could be lower, but it's not 7.4 anymore. And remember, this has to be different enough to matter, all right? If it's a little bit higher, nobody cares. If it's a lot higher or a lot lower, that's what different from means. If it's a lot higher or a lot lower, well, then people care. All right, so drawing my picture here, all right, I have a curve. I want a rejection area of 5%. Now the problem is I want the total rejection area to add up to 5%. Now I need a two-tailed test. It could be lower, the average could be lower, the average could be higher. So I need to shade some on the left and I need to shade some on the right. All right, I want to shade a total of 5%, but I'm going to split this exactly in half. I'm going to put 2.5% over here and 2.5% over here. That's what alpha divided by 2 means. I'm going to take the 5%, which is going to be the total shaded area. I'm going to split it in 2 parts and put an equal part here and an equal part there. So that 5% split in half is 0.0250. You can kind of see it here. If you just look at the 500, half of 500 is 250. It kind of makes sense, but you can do it on your calculator. 0.05 divided by 2 will give you this number right here. All right. Now, the question is, if I want 2.5% here and 2.5% there, where do I draw this line? So I got to look up that T number. All right, again, you can do this several different ways, but the easiest way is to come over here on the left side and try and find the t number that gives you this area. All right, try and find the t number that gives you this area. So if you're doing it on the calculator, I want to do a backwards t. I want to do an inverse t of 2.5%, and it will tell me what that t number is. So on the calculator, if I want to do a backwards t, I do second distribution. I choose inverse t, that means backwards t. That means give them the area, 2.5%, degrees of freedom 35, and then just paste it into your window, hit enter one more time. And it says you want to start shading at negative 2.03. All right, so we're going to start shading at not only negative 2.03, but at positive 2.03, because that'll put 2.5% on the left, and that'll put 2.5% on the right. Now you can do the same thing in the table. All right, I want a 5% critical region, but I want it to be a two-tail area. So I'm doing a two-tail graph, and I want 5% shaded. So I come over here to 5%. There's 5%, two-tail area, and I want 5% shaded. And if I scroll down to the degrees of freedom, it'll tell me where to start coloring. So I want to scroll down, 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 down to, let's see, what was it, 35, and there it is right there, 2.03. Since it's two-tailed, I want to do negative 2.03 and positive 2.03. All right, so I draw the line at negative 2.03, shade to the left, that's the left tail, 2.5%. Draw the line at positive 2.03, draw the line, shade, that's the other 2.5% for a total of 5%. All right. Now I just got to calculate my test data and see if anybody cares. All right. So my test statistic, T star, do the math. This is what I came up with. This is what the accepted belief was. And if I divide it by the standard deviation, it'll tell me how many steps left or right to place my dot. So I came up with 2.118. That means my test dot, my test statistic, is about just a little over 2 steps to the right. Here's 0. There's 1 step to the right. There's 2 steps to the right, and a little bit more. All right. Now this is getting kind of close here. My line is at 2.0. My dot is at 2.1. So my dot is just a hair further to the right. So my dot does land in the rejection region, just barely. Just barely. So I can just barely reject what they said. I'm right. All right. I ran a test. I measured 36. All right. I measured 36 people. I ran a test and I placed my dot here and my test was successful. I can now say that you are wrong. All right. I can say that no, this is no longer true. It's not believed to be 7.4 anymore. It's actually, I can say it's higher. But all I was trying to prove is just that it's different from, significantly different from. All right, so we choose to reject the accepted claim, the null hypothesis. And we say there is enough evidence, because we won this one. I get to reject what they said. I found enough evidence at 5% to conclude that. And then just copy your challenge from the story. The drug has significantly changed. They said changed either way. I like to add significantly changed the mean pH level of the blood. All right, let's do one more now. The only difference in this problem is they don't tell you the sample standard deviation. You actually have to calculate this on your calculator. Now you can do it by hand if you want to. If you're going to be like a statistics major, you should probably practice calculating, your average and your sample standard deviation by hand, but I don't want to. I just want to use the calculator. So this says they're measuring the thickness of slabs that avalanche, and they're measuring between 2 areas. I'll let you guys read that. But it says a random sample of avalanches in the spring give the following thicknesses. I need to put these into my table, and I need to have my calculator calculate some one variable statistics. That'll give me all the data that I need right here. All right, so we're going to grab our calculator, and to get to the table, we hit Stat, and I choose the first option there, Edit, and I put my data into list 1. Whoops. Okay, so there's my data in list 1. You guys can do that. After you get your data in list 1, you press Stat again, And this time you go over to calculate, and we want it to do option number 1 right there, one variable statistics. Now it's asking me, it's just double checking. It says, is your data in list 1? Yes, it is. Don't worry about that. Get down to calculate and make it calculate. And there's basically everything we need right here. Okay, X bar is 61.8125. So my sample average, if I add these guys up and divide by 16, if I add these up and divide by 16, my average is 61.8125. Give or take, that's what standard deviation is, give or take 10.647, etc. There's your 10.647, your standard deviation. So X bar is 61.8125. Standard deviation is 10.64718.273, and they went ahead and told you that you have 16 values, n equals 16. All right, now that we have that data, the rest of the problem is the same. They want us to check and see if it is different from what is assumed to be true. If you read up here, it is assumed that the thickness is 64. This is the accepted belief. So the accepted belief, the null hypothesis, is the thickness is 64. I did my own sample right here, and I came up with 61.8. It looks like my sample is thinner than 64. This is 64 inches, that's 62 inches. Mine appears to be thinner. I could challenge that, no, it's less than 64, but they want us to simply challenge that it's different from. So I'm going to say, okay, the accepted belief is 64. The null hypothesis says the population average is usually 64. My challenge, the alternate hypothesis, says, no, the average is not 64. It's different from it. Could be lower, could be higher. Let's run a test and find out. We'll find out if my data is significantly different from what is believed to be true. All right, draw your pictures. Now remember, they said 1%. I skipped over that. 1% level of significance. That's going to be tiny. So this is going to be a two-tailed test with only 1% of the curve shaded. All right, now remember, I want to split it in half. So half of 1% is a half of a percent. If you guys kind of look right here, look at the 100, think of that as 100. Half of 100 is 50, so it kind of makes sense. But just take your calculator and do 0.01 divided by 2, and you'll get 0.005, either way. So what I'm going to do is I'm going to shade half of a percent over here and half of a percent over here. That adds up to 1%, which leaves 99% in the middle. So I don't have very much area on the tails at all. All right, how do I look this up? I've showed you several different ways. I'm just going to grab the table. I'm going to say I'm doing a two-tailed test, and I want 1% of the area covered up. So I grab my table. I'm doing a two-tailed area, and I want the area to be 1%. That's 0.01. And then I go down to my degrees of freedom, which I forgot is 15. So 1% two-tailed test, go down to 15 degrees of freedom. That is right there. Looks like 2.947 to the right and 2.947 to the left is where I shade. Okay, so I start shading at 2.947. That's almost 3 steps. 1, 2, there's 3, so 2.9 is a little short of that. 2.9 is where I draw the line, shade to the right. And then 1, 2, 2.9 to the left, which is negative 2.9. I draw the line, I shade to the left. That gives me a 0.5% rejection area here and a 0.5% rejection area there. All right, that's tiny. It's not very big. Now I run my test and see where it lands. All right, my test turned out to be negative 0.822. So I put my dot, just remember that star, the test statistic, that's going to be a dot on your graph. I put that dot 0.8 of a step to the left. Here's 0, there's negative 1. I just want to go 0.8 of that. So it's about right there. Put a big old dot there. That's your test statistic. This is based on your data. This is where it landed. And now you can look at your picture here and make a decision. It obviously landed here in the white. So we lost that one. We have to accept what is believed to be true. We have to accept that the average is 64. The average thickness of these slabs is 64. So I have to accept what they said. I have to accept H0, the null hypothesis. But what I'm going to say instead is, instead of accept H0, I have to admit that I failed to reject it. I tried to say it was wrong. and I failed. That's how we have to say it. And then finally, just interpret it for, grandma or whoever's reading this. There's not enough evidence. I failed. I didn't gather enough evidence to conclude that, and then restate your challenge. The slab thickness in Vail is significantly different from that in Canada. All right, guys, that's it.